As always, I'd like to start with announcements. There's a homework 0 that's due on Canvas today. Many of you finished it. If you haven't, please get it done today. You get 2 attempts for doing the homework, and it's the highest score stay. And this is supposed to be testing or just getting you reacquainted with your prerequisites. And if you need any resources, check out the website. There were a couple of students who got permission codes, and I think, to the best of my knowledge, everyone who wanted a permission code for this class has one. If you still need a permission code, come see me after class. And the first real homework 1, will be available sometime today. Ideally, sometime today or tomorrow morning. We are trying to work out the logistics. Any questions about any of these things? If you need it, you know what it is. So basically, it's if you want to register for the class and you're having trouble, then I need to let you in. Yes.
Most assignments were given like a week to complete them.
No, so homework 0 is an exception in that it gets a week. Any the bigger homeworks get 2 weeks, and anything that's like homework 0 in that it's a Canvas quiz gets 1 week.
And then they typically do on Tuesday, or
it's every 2 weeks. It looks like it's going to be due on Tuesday,
okay.
But I know that after the spring break, things might change because there's a 1 week offset.
Yeah.
Things might change after spring break. I tend to not want to give out a homework the first lecture after break. We'll see. Other questions? Another set of announcement is about office hours for TAs. We have the rooms and such things ready. We have Purbit here will have his office hours on Mondays at 3 p.m. 3 p.m. right? Yeah, 3 p.m. In MEV 3145. If you need help finding that room, talk to the front desk of the CS department. And Oliver, sitting right there, will have his office hours on Tuesdays just before class. And my office hours are going to be Thursdays at 10 a.m. in my office. Feel free to come to any/all of our office hours. Otherwise we're just sitting there on our own. And the other announcement is there's an event coming up. Next Friday, there's going to be the Utah Data Science and AI Day. It's a day of talks and networking events and such things. There's also going to be a career expo. There's a keynote talk by Dieter Fox, who does robotics in University of Washington and NVIDIA. His talk is going to, I think the title of the talk is Where is RoboGPT? It promises to be interesting. I believe that if you register ahead of time, you can also show up for breakfast at 9 a.m. I know that 9 a.m. is too late for some people and too early for some others. You be the judge of your own preferences. All of this is happening in the Union Ballroom. On Friday, if you need more information, go to datascience.utah.edu. I'll probably remind you once more next week. And if you have any questions about this, go to the website. Any other logistical things you want to get out of the way before we launch into the technical stuff? Looks like there isn't any. So let's talk about decision trees. Today we're going to introduce, today is the start of a new topic, namely decision trees. And this is going to be the first of several learning algorithms that we'll encounter in the semester. And there's a reason why I like to introduce decision trees early in the semester. It's one of the older machine learning topics. It used to be one of the topics that was the focus of a lot of attention till maybe the 90s, and it's still useful to have this in your collection of tools. Every time I introduce a new learning algorithm or a new hypothesis class, you should think about, you should have the following topics in your head, because these are the things that we need to address. No matter what algorithm I present, no matter what new class of functions we discuss, it's always worth thinking about practical details of how you fashion your problem into a machine learning problem that fits that, that solution strategy. We'll be looking at a bunch of solution strategies. For the same class of functions that you want to learn, there might be different kinds of learning algorithms. So the choice of which learning algorithm you use might be a practical decision. You should also think about how to represent your inputs in the domain that you're working in as a machine learning problem that fits this class of functions. So for any algorithm that we encounter, you should ask, how do you define success for that algorithm? In particular, remember, the most important lesson from the first week was the idea that learning requires generalization. So how does this algorithm that we encountered favor generalization? How does it lead to generalization? Sometimes algorithms encode certain properties that naturally lend to generalization. Sometimes they do not, in which case you have to do extra work. And also, the other thing that we have to worry about is the computational thing, computational question. How long does learning take? The computational complexity of learning. We are writing programs. You will be writing programs to implement these algorithms. So you need to worry about how long these algorithms will take. So typically, we'll be thinking about computational complexity using the language that you use for analyzing any algorithms. Going ahead, we'll be looking at different hypothesis spaces and different learning algorithms. Today, we'll be looking at decision trees and an algorithm called ID3. Then we'll be looking at linear classifiers. We'll be looking at multiple different, the combination of multiple different classifiers, nonlinear models, nearest neighbors if time permits. And in each case, you need to think about these same issues. How long does learning take? How does this particular class of functions, or how does this particular learning algorithm favor generalization? What is the learning algorithm itself? What is it actually doing internally? And how do you represent examples? Today, we're going to look at decision trees. And hopefully, we'll wrap up the ID3 algorithm as well by the end of today's lecture. But for all of these cases, you need to consider the same questions. So this lecture, this unit, is about decision trees. It's a new hypothesis class that, well, it's the first of many hypothesis class that we'll look at. And you need to think about what these functions are. A hypothesis class, remember, is a function that maps an instance to a label. Mathematically, it's a function. So how is that function defined? Then we'll look at the learning algorithm that takes a data set and produces a function that, for some reason, it claims is the best in that set of functions. And typically, here and for future algorithms, we'll look at the vanilla version of the algorithm, the simplest case, and then we'll look at practical extensions that make this algorithm more useful in real-life situations. So let's start with the representation. What are decision trees? How many people have seen decision trees before? Many of you. Well, some of you have not. That's okay. But it's a very easy idea, and let's see how we can let's look at what they are. The fundamental question comes down to, how do we represent data? You can, of course, represent data as a big table. This is what databases do. Databases are big tables that contain rows of records, rows that represent records, and columns that represent different fields. So you have, this is the a version of the badges data that we saw before. There are two columns, name and label. So you can represent your data like this. And this is what you might see in a database class. Alternatively, instead of representing data like this, you can also compute additional features for each row. So there's a feature called is the length of the first name greater than 5? And it's a yes for Leslie Cabling, it's a no for Eric Baum. Here. So you could compute features, right? And you can imagine that there are many number of features that you can invent and compute and store in this form. Now imagine that you've decided that you don't want to really store the name column at all. You only want to store these 4 features and whatever is the label. A question to think about is how many, if you have only these 4 features, how many unique rows are possible? So you have one feature that is, does the name have a punctuation? It can take 2 values. Another feature that says, what's the second character of the first name? Assuming ASCII and English names, well, assuming ASCII, how many characters are there? 26. The length of the first name is greater than 5. That's a yes or no. So it takes 2 values. And is the first letter the same? Is the first letter of the first and last name the same? That's a yes or a no. That takes 2 values. So how many unique rows are possible? You don't need to tell me the number, but you can just tell me how you get them. Just multiply all of them together. And if any of you is faster at math than me, you might even know what that number is. I don't. So if you get rid of the name column, suddenly the table looks a lot simpler. No matter how many names exist in the universe, there are only these many columns that, these many rows that the table can have. So the table seems to have shrunk. Or has it? So, okay, that's the number. Instead of these 4 features, imagine there are 100 features. And let's say all of them are binary, yes or no. How many unique rows can exist? Yes. Yeah?
2 to the power 100.
So it's 2 power 100. Suddenly, that doesn't look particularly favorable. Doesn't look like there is it's going to be an efficient data store. By the way, how did we get 2 power 100? You're multiplying 2 100 times. Each feature can take 2 values, and each feature's yes or no is independent of the values that are in the other feature. That's why you're multiplying them. So if you want to store every possible row, this is too large. And so we need to figure out a more efficient way just to store this data. We're not talking about building classifiers or such things at this point. It's just about representing this data efficiently. And one answer to this question is a decision tree. A decision tree is a hierarchical data structure. It represents this kind of a table using this sort of a divide and conquer strategy. It turns out that this representation, this sort of an efficient data representation, also can serve as a hypothesis class for both classification and regression, and we'll see how. Because this data structure can serve as a hypothesis class, the whole point of decision tree induction or decision tree learning is to find a decision tree that represents a data set and then use it on future examples. Any questions about where we are? Let's formalize this a little bit. For our purposes, a decision tree represents a family of classifiers where for instances that are represented by features. And for our purposes, in all cases, instances are going to be represented by features. It's a tree data structure, which consists of nodes and edges. Every node in a decision tree is a test for a feature value. So something like is name or is the length of the name even? This could be a yes or a no. And that partitions the data into two parts. And then so we have one branch coming out of the node for every value that the feature can take. And the leaves in this tree represent the labels. Let's look at an example. I mean, this is a little dry, so let's look at an example. So imagine that you have a data set consisting of shapes. And there are three labels. Some shapes are called an A, some shapes are called B, and some shapes are called C. Before we do anything, before we build a decision tree or anything, just a quick guess. What do you think is the label for a red triangle? So there's one person who says B. Anyone else? A few heads nodding. Did someone say A? No. Most people seem to suggest B. Why?
Between all the labels here, red shapes only show up under label B. And also triangles only show up under label B.
Yeah, that seems like a reasonable thing. And so let's see if our decision tree eventually does this. Also, what are some features? What might some features be for this data? Yes.
The color of the shapes.
The color. So you have red, blue, and green. Other features? You've said something before, so someone else. Yeah.
The number of sides of each shape,
The number of sides of each shape, that's
like triangle, square.
basically it's the name of the shape,
Yeah.
right? There are only three here. So it's circle, triangle, or square. Square. These are good choices, especially because that's literally what I have here. And it makes my life a little easier. If one of you had said something complicated, then I'd have had to quickly remake my slides. So let's see if we can build a decision tree using these two attributes. So we can ask, what's the color of the shape? What's the color of that object? And we have three options, red, blue, and green. That means there will be three branches coming out of that question, one for each color. Now, notice that the minute you go down this path, we're done. If the color is red, we can directly say that the label is B. We don't need to ask the other question. So we're done. Because all the red things are here. Now let's consider the other side. For blue objects, you look at the shape. If blue triangles seem to be B, blue squares seem to be an A, and blue circles seem to be a C. So just looking at the color and the shape allows us to classify these objects correctly. And similarly, we can ask the questions about green things. There are green squares inside this box here. And so all green squares are B. And then there are green circles or ellipses or such things on the under label A. So all the circles are A. There are no examples that don't fit in this tree. So now what we have done is we've taken that data set and represented it efficiently as this decision tree. Alternatively, another way of saying this is we have trained a decision tree on this data set. What learning algorithm did we use? We just kind of picked a label, picked a feature color at the top, just partitioned the data, and then picked the next feature and kept going till we partitioned the data completely. We'll see a nicer version of this soon. But before we talk about that, we can use this decision tree for prediction. There were no red triangles in this data. So we can ask, what would the decision tree predict for red triangles? And the answer is B. This is an example of generalization. This is an example where this is almost a trivial example. we are able to assign labels to things that we've never seen before. There were no red triangles in the data that created this tree, yet the tree can assign labels to red triangles. Yes,
Is there a reason why anyone would choose color first or why you choose color first?
there is a good reason. I chose color first mostly because this is a choice that I made 10 years ago. That was because I think Tom Mitchell did that in his textbook, or someone. So there's no reason for that, but that's a very good question. So let me repeat the question. Is there a reason for choosing color at the root of this tree rather than shape? Another way of asking this question is, what is a good motivation for picking one label at the root of a decision tree? It turns out that becomes the most important question to decide this learning algorithm. And we'll spend a fair amount of time talking about that. Other questions? There's another question here waiting to be asked. Do you see something problematic about this tree? Yes. That's right. I could have, instead of asking a label for a red triangle, I could have asked, what's the label for a green triangle? What is the label for a green triangle based on this tree? At this point, you have no answer because, really it's an exception. If you follow the path down this side, green, the shape question does not have an edge going out for triangles. So what do we do there? I'll let you see the data once more. And can you guess what label you might assign to green triangles? Or can you guess what label you will not assign to green triangles? C. There doesn't seem to be any evidence for assigning a C. But between A and B, you need to make a choice. You're making an assumption. It turns out that this assumption will show up also in the decision tree learning algorithm. There is a certain choice that you'll make in your implementation that will decide whether you'll assign your tree will pick A or B eventually. And we'll keep that question in mind. When we come to the learning algorithm, we'll visit that choice once again. Yes.
So with the blue, you could say like, oh, there's a blue shape in each one.
Mhm.
Why wouldn't there be a green shape in each one?
That's an interesting choice. It's an assumption, right? There may be, or maybe, maybe blue is the exception. We'll see what it comes down to eventually, but really it's a statistical question. We'll let the data make the decision. Okay. So we talked about green triangles. The other thing that you should ask yourself every time you encounter a new hypothesis class is what kinds of mathematical functions can be represented by this set of these set of classifiers. It turns out, well, decision trees are discrete functions, right? I mean, there are a countable number of leaves that any tree has. And suppose you have, instead of 3 choices, this is a multi-class classification problem where, example where you have 3 labels, A, B, C. Instead, let's say you have 2 labels, just plus and minus, or true or false. You could ask what Boolean functions can you represent using decision trees? And the answer, it turns out, is every single Boolean function can be represented by a decision tree. I'm not going to go into the construction here, but one way of thinking about it is, let's consider this path down the tree. So you have color is blue and shape is triangle. If the color is blue and the shape is triangle, the label's a B. If the color is blue and the shape is a square, the label's an A, and so on. So the final label the tree is equivalent to a complicated Boolean function that is, this is what I've just drawn the box. I've drawn the box around the path following blue triangles. I could consider every path from the root to the leaf and take a big AND of all of them, and it turns out that's a Boolean function. I'll leave it as an exercise for you to think about later, but it turns out every single Boolean function can be represented by a decision tree. In other words, the set of decision trees is at least as large as the set of all possible Boolean functions. How many Boolean functions are there if you have n features? If you have n features, you have a truth table with 2 to the n rows. How many Boolean functions are there? This is an interesting question that I want to spend a little bit of time on. So let's consider two features or two features. Yeah, so let's call it A and B. This can be 0, 0, 0, 1, 1, 0, or 1, 1. These are the only rows in the truth table for a Boolean function. There's a certain function that I'm going to call f0. F0 assigns false no matter what the input is. F1 does this. F1 is takes the label value 1 if both A and B are 1. It's a conjunction. F2 assigns the value 1 if A is 1 and B is 0 and 0 otherwise. F3 does this. You see what I'm doing here? I'm basically enumerating Booleans vertically for 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, and so on. So how many possible columns can I have?
2 to the n to the n.
2 to the,
2 to the n.
in this case, 2 to the 4. Let's make it simple. There's no n, right? There are 2 power 4. How did I get 4? 4 because there are 4 rows here. There are 2 square, or more generally, there are 2 power n possible rows, and there are 2 power n possible ways I can fill up things here. And so the number of possible Boolean functions is 2 power n. The thing is, every single Boolean function can be represented as a decision tree. So the number of decision trees is at least as big as 2 power n. It's a massive number. And it turns out that's going to be problematic. And we'll come to that most likely on Thursday. Any questions about this? About this argument that I have here? So Boolean functions can represent all kinds of every possible Boolean. Sorry, every Boolean function can be represented by a decision tree. In the way I presented this, the labels are discrete categories, right? Like ABC or plus minus, true, false. I could put anything in the label. I could put numbers in the label, real numbers. Now suddenly, if I put real numbers in the label as the leaf of the tree, then you get functions that take features and produce real numbers. I could even put real valued functions as labels, as the leaves of the tree. So I don't want to go into that level of complication, but it turns out that there are simple extensions to this data structure that also allow for regression. And between these sort of regression and classification trees, we have a well-studied family of methods for handling noisy data, for handling missing features, and it turns out you can also there are heuristics to help with generalization, and we'll look at each of these things as we go along. One thing that we did not look at was numeric features. All the features that we've seen are discrete. The color can take 3 values, red, blue, green. Shapes are either square, there are 3 shapes, right? Yeah, there were 3 shapes. We looked at the second letter, which can take 26 values. How do we handle numeric features? Some features can be numbers, right? The area of that shape, for example, could be a feature. Any idea? Yes.
Maybe you could put the value in baskets, like between 0 and 5, to this feature, 5 and 10.
You're bucketing them.
Yeah.
You're essentially creating these ranges and saying that's one idea. Others? Or anyone in support of that or not? Turns out that's the standard thing that's done. What you do is you discretize these features and you move from this numeric space to these buckets. One thing you cannot do is have one edge coming out for every value that that's observed. Imagine, for instance, you have area. This is your feature, and let's say I put 1.1. How many? Well, let's also put 0.8. Just for how many values? How many branches can come out of this thing? Infinite, and not even the good kind of infinity. It's uncountably infinite. So we cannot handle real value numeric features as it is. We need to somehow convert it into discrete groups. And the most common strategy for that is to discretize them with thresholds. Here's an example. Imagine that we would like to represent this partitioning of this two-dimensional plane. So you have two features here. I'm calling them X and Y. We want to somehow create a decision tree that represents this partitioning. One way of doing that is we could ask, is the value of X less than 3? That corresponds to everything on this side of the line that I just drew. If it is less than 3, then you go down this path here, which corresponds to the region between X is 0 and 3. And then you ask, is Y less than 5, which is below here? It turns out that if X is below 3 and Y is above 5, everything's a plus, so we can just directly say it's a plus. And so on. I mean, I'm not going to go through every branch, but basically by slicing the space with, here I have just used axis parallel rectangles or axis parallel lines to separate out the X and the Y. You could do other kinds of complicated bucketing that says that X plus Y is greater than 5. If X plus Y is greater than 5, then the label is something, if you had a reason for that. But by doing this, notice that the boundaries between the pluses and the minuses, the region that's called plus and the region that's called a minus, is non-linear. This boundary between two parts of the instant space that have different labels is called a decision boundary. And it turns out decision trees are one of the methods that we'll encounter that allows for non-linear decision boundaries. This may not seem like a big deal right now, but I just want you to keep this thought in mind, because eventually we'll spend a lot of time talking about linear classifiers and linear models and such things, at which point it's worth knowing that there were an older class of methods that were non-linear. Eventually, we'll drop that assumption of linearity when we go to neural networks. Okay, so quickly summarizing this part of this unit, what we saw was a data structure called a decision tree that can represent any Boolean function. And it's a way to represent a lot of data. And it's a fairly natural representation. You can think of it as playing 20 questions. You ask a question about something, and you essentially at prediction time. At prediction time, you ask a question about a feature. If the feature takes a certain value, you just go down the tree and then ask the next question. This means that making predictions with a decision tree is very easy. You just go down the tree, and the leaf of the tree is always a label. one issue is that given any data set, there are multiple decision trees that can represent that data set. Why? Think of the circles and the triangles. Yeah.
Changes in structure of the tree.
Yeah, it's related to the question of how do you know that why did I choose color at the top of the tree? Had I chosen shape at the top of the tree, you would have gotten a different tree. So the changing the features that you look at the top of the tree at every position can change what the tree looks like. Any questions? If there aren't, oh, there's a question on Zoom. You can either unmute yourself or you can.
Hello, Professor.
Can you
So
type it? Because I think my speaker, if you're typing your question, I'll just switch slides while you're doing that, and I'll come back to you in a minute. The next thing we look at is how do we actually learn these trees? So this is really the main point of this lecture, and so we're going to spend a fair amount of time looking at how decision tree induction or tree learning works. Let's talk about learning decision trees. There's an interesting question on Zoom. I'll read it out. We are reaching the same decision, even though the structure of the decision tree is different. So can we actually say that these two decision trees are different from each other? That's an interesting question. Let me paraphrase that. Let's take that example with the shapes and colors. If I had chosen the feature color as the root, I get a tree. If I had chosen the feature shape as a root, I get what looks like a structurally different tree. But these two trees will give exactly the same labels for all the training examples, because the training examples were used to build the tree. So they will agree with each other on the training examples. So can we actually say that these trees are different from each other? It turns out that they need not be functionally different from each other. They could be structurally different, but not necessarily functionally. However, what we might find is choosing a different route can lead to different labels for unseen examples, for examples that were not in the training data, because certain paths might not even be valid anymore. So while changing the feature at the top of the tree changes does not change any label for the training data, at least in what we've seen so far, it may change the predictions made for future examples. That's a good question, though. Okay, now let's look at how we can learn these decision trees, and these issues that I just mentioned about picking the root of the tree and such things start mattering more. We'll be looking at an algorithm called ID3. It's a greedy heuristic. It's one of the older decision tree learning algorithms, and most subsequent learning algorithms for decision tree essentially build on top of ID3. A brief history of research on decision trees. I haven't been able to find who invented decision trees, or which. There isn't a definitive citation for who invented it, because it's such an obvious idea. It's like asking who invented the 20 questions game. But there's a fair amount of work that existed in psychology in the 1960s on trying to model human concept learning using decision trees. And a big jump in this area happened when Ross Quinlan developed an algorithm called ID3. ID3 stands for Iterative Dichotomizer 3. Don't ask me anything more about the name. And it uses something called the information gain heuristic, which we'll look at in some detail. And the ID3 algorithm and the whole decision tree literature led to a lot of, ended up pushing the state of the art on what were called expert systems in the 1970s. Expert systems in the 70s are like what deep learning is today. Everyone wanted to do expert systems. In the mid 80s, a bunch of statisticians, Leo Breiman and Friedman and their colleagues developed something called CART, classification and regression trees. And throughout the mid 80s and 90s, there were a lot of advances on making these class of algorithms, ID3, CART, and these things, more robust to noise, heuristics for handling missing features, and such things. And also there was a lot of theoretical analysis of the properties of these kinds of algorithms. There were, of course, updates to these algorithms. I think there's an algorithm called C4.5 or C5, which are essentially grown-up versions of ID3, which are actually more commonly used, but we won't be looking at the details of that. That's basically more bookkeeping. We'll look at ID3 in some detail. Decision trees also became very popular once again in the early 2000s, early to mid 2000s, because of this idea of boosting. We'll look at boosting much later, but the intuition here is rather than training one tree that fits a data set, you train many trees and think thousands of trees that fits maybe subsets of the data, different randomly chosen subsets of the data set. And then your final decision is actually consensus between these 1,000 trees, the final prediction. Turns out that's a very, very robust way of doing things. And the heuristic, the common, the folk knowledge around 2005, 2008 was, if you really want the state of the art for machine learning, for applying machine learning, look no further than this sort of a committee of trees, because it's very hard to do better than that. I'm not sure if that's necessarily true today, but once again, it's a useful tool to have in your toolkit because these are incredibly efficient and easy to implement. That's as much of a history lesson that I'm willing to spend time on. So let's get into some details about the learning algorithm. I'll use this example that showed up in the original paper by Quinlan on playing tennis. Suppose the task is the following. Given some observations about the day, like the weather, the outlook, temperature, humidity, and whether it's windy or not, the goal is to use a decision tree to decide whether I should play tennis today or not. Anything to avoid actually going outside. So the outlook can take three values. It can be sunny or overcast or rainy. The temperature can be hot, cold, or mild. Humidity can be high, low, or normal, and the wind can be strong or weak. And on any day, you measure these things. You give it your decision tree classifier, and it decides whether you should actually play tennis that day or not. Once again, don't do this in real life. If you want to play tennis, play tennis. But let's say that you collect a data set with over a period of time. There are 14 examples here. And for any one day, let's pick day number 8 here. The outlook is sunny. The temperature is medium. The humidity is high. And the wind is weak. On that day, for some reason, you did not play tennis. And you can collect the data. And this is going to be a running example for looking at this algorithm, the ID3 algorithm. Our goal is to learn a decision tree that represents all of these variables. The decision tree algorithm is a batch algorithm. What that means is all the data is processed as a single batch. It's not like if day number 15 comes in, it's not like you just take that last example and then slightly edit the tree that you just trained. You start from scratch again using the entire thing. And the ID3 algorithm recursively builds a decision tree top down. to give away the punchline, it turns out the ID3 algorithm will build this particular tree that's on the slide. If the outlook is sunny and the humidity is normal on that day, you play tennis, for example. The key decisions that you need to make in order to construct this tree, there are only two decisions, it turns out. The first one is to decide what feature goes at the top of the tree. What makes us choose outlook at the top of the tree and not any of those other features. The second decision to make is once you have decided to split the data, split on outlook, what do you do for each value that the feature takes? If you can answer these two questions, turns out then you can actually build the whole tree because you keep asking this question again and again. You partition the data here. Now, the thing that I've circled there is a smaller decision tree. Once again, you ask what feature goes on top. In this case, it was humidity. And then you ask what to do for each split. So the algorithm is recursive in that all you need to do is identify what feature goes at the top of the tree and what you do for each split. Any questions about this? I mean, I've not told you what the algorithm is, but this is it's just a preview of coming attractions. Without further ado, let's just look at the algorithm itself. So this is a basic decision tree algorithm. There are many variants of this. The function called ID3. It takes a data set. I'm calling it S here. S takes labeled examples and a collection of features, attributes that are measured for each example. So it's like, what are the names of the columns that are that we have at our disposal. Let's first consider all the simple cases. The simplest case is you have a data set, and let's say every single example in the data set has the same label. There's no need to build a tree. Every single example has that label. You just return a leaf node with that label, right? There's no need to partition the data anymore. If you play tennis on every day, irrespective of whether the weather is whatever is happening in the weather, why do you actually need to look at any feature? You just say yes. That's the easy case. That's the base case of the recursion. The interesting thing happens otherwise. If all the examples do not have the same label. Oh, by the way, this might be a good time to let you know that you'll be implementing this algorithm for your first homework. So as we are going through this, also think about how you'll be implementing it. So what do you do otherwise? Well, we need to build a tree. To build a tree, we need to construct a root node. The root, and then the rest of the data structure just hangs out of the root node. So at the end, whatever we do here, we're going to return the root node and the tree that's connected to it. So the first step is we need to decide what feature, what attribute goes on the root. And one way of doing that is to, let's say we have some way, we have not yet talked about how. Let's say we have some way of deciding which feature best classifies the data. And if a certain feature, if we are able to identify such a feature, we call that feature A. It could be something like humidity or outlook or shape or color or whatever. And that feature can take multiple values, right? The shape feature could have taken 3 values, circle, square, or rectangle. In this case, let's say that it can take a bunch of values. We're going to iterate over all of them. And let's say we are currently considering a value B that the feature A can take. By the way, if this is abstract, we'll actually look at an instantiation of this algorithm on this data right after this. So, we'll look at this a few times. So one of you feel free to hold your questions till we get to that. So for every feature that the attribute takes, we need to add a branch because that's the definition of a decision tree. Nodes represent tests. That's the root node. And the branches correspond to values that test can take. So we add a new branch for that particular feature taking the value v. Now, more importantly, did you have a question?
Yeah, so with respect to, how do we know which attributes best correlate this?
I know, right? That's the main question, and that's what we'll spend most of our time on. I'm just giving you the scaffolding for the algorithm, and that particular thing that I've underlined there is the one part of the algorithm that we need to explore next. That's a good observation. So we have created a root node with the value that tests for the feature A, and it takes multiple values, and we are currently sitting on value V. Remember that we had a data set S. Every row in the data set could have had that feature A, and it can take multiple values. Consider only those, let's consider only those examples where this feature A takes the value V. It's a subset of the examples, right? So let's call that subset S sub V. SV is the set of examples where the feature A takes the value V. What do we do now? Well, it's entirely possible that there's not even one example in the data set that where the feature A takes the value V. This is like those green triangles. It's entirely possible that the subset S sub V is empty. So let's first handle that case. That's the easy case. What happens? What do you do if SV is empty? So we have a set of examples, capital S, and we have a feature A, and we don't have a single example where that feature takes that value V. We still need to give a label for, it's possible that there might be an example in the future where that feature takes that value. So we need to assign a label. What label could we assign? And this is going back to the question that you asked before, the green triangle. What label would you assign to this case where a certain feature, let's consider feature A, let's say it takes 3 values, A, B, and C. And let's say there are 100 examples here, there are 100 examples here, and there are 0 examples here. What do we do for that branch? Yeah.
Just take the one with more examples, or one with 34.
You could, so the suggestion was you could take the label that has more examples, and if it turns out that both of them are equal, then you just randomly pick a label. So let's give these, let's make this more concrete. Let's say if you go along the set S has 200 examples here, right? S has 200 examples, and let's say there are 90 plus and 110 minuses. And those got partitioned into A and B this way. Well, in this case, it seems like if you do not have any information, the safest choice is to say minus. Because there are more minuses in this data set overall, and you really want to, you'll get, if you're randomly guessing, you're better off guessing the more frequent things. That way, you're more likely to be right in the future. So if the set SV is empty, then you add a leaf node with the most common label in the superset S. And the reason for that is it can lead to better generalization, or at least it can lead to fewer errors in the future if the data follows the same distribution. Questions about this? Yeah.
So when you say like the most like common value, you're saying the most common value in S?
The most common label in S.
Right, so like in your example,
Here.
the negative label appeared most, right?
Yeah. Yep.
So now we just label as negative.
We'll just
If
say,
SV is negative, then
no, we won't say SV is negative. We need to attach a leaf node to the tree, right? So we'll attach we need to assign a label here. We'll say, if you take this path, the label is a minus.
Right.
And then we still haven't decided what to do in these two parts. You don't look convinced.
No, I framed my question correctly, but yeah, you answered it.
Okay. Other questions? Yes,
You assign it that value.
you assign it the label. The label. Remember that the leaves in a decision tree are all labels.
So in this example, A be like plus and B be minus.
A, B, and C are actually features, feature values. So it's like the color is red, blue, or green. So A is red, B is blue, G is green. No, C is green. And we did not see a single green thing. We still need to give it a label. So we'll create a leaf node and call it a minus. In the future, if you are ever coming down this path here, if you're ever coming down this path, future examples will get a label minus.
If it's ever, so if you ever get a plus, then you just separate the minus.
You can't do any more training in the future.
Okay.
Once you've trained the tree, you're done, because this is the tree that you're going to evaluate for all the. This is during training. Let's look at an example and we'll work through the example, and hopefully this will get clarified. I think I know what you're asking, but I don't want to answer it because that's going to go into the weeds, and we'll be looking at that in the example anyway. But the intuition here is, if you do not have any evidence for a certain feature taking a certain value in the data, then the most reasonable thing to do is, for examples of that kind, if future examples take that value, you give it the most common label, so that you are less wrong on future examples. Was there a question at the back? Yeah.
Let's say we assign minus, but later we know that it should have been a plus because C is of that type. So can we do anything with that?
How do you know it's going to be a plus?
Let's say we know what kind of attribute C is, so.
Then you're retraining the decision tree. Then essentially you're getting more data and you're revisiting the question of what the shape of the tree should look like. And at that point, because this is a batch algorithm, you might as well start from the beginning and start, maybe you're changing the statistics of the data, might as well just revisit the thing from the top. So the short answer for if there are no examples where the feature A takes the value B is you add a leaf with the most common label. So now we are in the case where there are some examples where the feature A takes that value B. So we have this set S sub V. S sub V is a non-empty set of examples. And I need to construct a decision tree using a set of examples. So we need an algorithm that can take a set of examples and produce a decision tree that we can attach to this particular branch. It turns out we have an algorithm. That algorithm is called ID3. So at that point, if we have a non-empty set of examples, we make a recursive call to ID3 with a subset SV, and we are no longer allowed to use the feature A because we've used it up. So we give it all the features except A. And we make a recursive call to ID3. We get back a tree. We attach it to that branch. One of the worst ways of learning an algorithm is actually to just watch someone walk through that algorithm on slide. So let's actually instantiate this on the data that we had, because it's much more interesting to do that. And really, the correct way to understand this is actually to implement it and have it, play with data. But very briefly, the most important question here is, how do you pick the root attribute? Turns out I cannot actually instantiate this algorithm until I answer this question here, because that's the only non-trivial choice in this algorithm. So the most important question here is to pick, we need some mechanism for deciding which feature we are going to split the data on. our goal, or Quinlan's goal in designing the ID3 algorithm, was to create decision trees that are as small as possible. And the intuition here is, imagine that you have a data set and there's a small decision tree that perfectly explains the data, and a very large decision tree that also perfectly explains the data. Between these two, it's preferable to choose the smaller one. Why might that be? Yes.
Quicker to run,
Sorry?
quicker to run.
There's an efficiency argument. It's quicker to run, but it turns out there's a stronger reason for this. Yeah.
Bridge, and being visually reason about the tree.
So the answer was, so the suggestion was, the smaller tree is more efficient. It's kind of related to the quicker to run. And the other thing is, you can actually look at the tree and understand. Imagine a tree with 1 million nodes, try printing that. Whereas a tree with 5 nodes, you can actually examine it. Turns out there's an even stronger argument than that. Yes. The suggestion is that the smaller tree can generalize better. Why?
So if you have incredibly bigger tree, you can specify some conditions on the sample. So that won't be general when you have a new one.
In a sense, yes. So let me elaborate on that point. And by the way, that is that's the answer I'm looking for. The answer is that smaller trees may generalize better. And the reason for that is, I'll answer this with an example. Imagine that you have a data set with 1 million examples. And let's consider 2 trees. Let's call them tree A, which is just, what is the value of the feature x0? If x0 is true, the label is false. If x0 is false, the label is true. That seems like an easy tree. Now let's consider tree B, which I cannot draw here because that tree has 1000 nodes in it. It's 1000D. It starts off with, like, if the day of the week is a Monday, and then it checks whether we are in 2025, and then it checks whether the weather outside is sunny. It checks for all sorts of things, and it just so happens that both of these trees perfectly fit the data. I would argue that the tree A, which is smaller, is going to do better on future examples because it's more surprising to find a small tree that perfectly fits the data as an explanation than it is to find a big tree that perfectly fits the data. Given any data set, you can find a large enough tree that perfectly fits it, because you will essentially keep partitioning on all the noise features. Imagine that you have, in this case, if tree A perfectly fits the data, only feature x0 is relevant. And the remaining, let's say, 999 features that were in the data are all noise features, but you can always keep partitioning the data to kind of get to a split where there's only one example that you classify. You can essentially keep splitting the data on noisy features. I'll come to you in a minute. And you will be able to perfectly explain any data set. Given a large enough tree, you can fit anything. The more complex, or another way, sort of an analogy here is, complex enough functions can represent any polynomial. With high degree polynomial, you can represent any data. Yes.
So is the purpose to try to get rid of any useless information or useless features?
The hope is that we only use relevant features. The hope is that we use only relevant features, and by relying only on relevant features, we are able to get smaller trees. Yes, at the back.
So when looking for smaller trees, are we trying to minimize the number of edges in our tree, or the depth of the tree, or the branching factor?
Either one. And we can't control the branching. So the question was, are we trying to minimize the depth or the branching factor or the number of edges? It turns out we don't get to control the branching factor because that depends on the features that we've chosen. If your feature is the number of the second letter of the first name, then it branches 26 ways. Whereas if your feature is Boolean, it's a two-way branch. So that's something we don't get to control. Given that we can't control the branching factor, really it turns out the depth of the tree versus or the number of features are essentially equivalent.
So if, with the example with the, whatever, the second letter.
Yeah.
So if we did that, so for, as the first feature we looked at, we'd have 26 branches on the first node, and then, you know, maybe a bunch of binary.
That's fine.
branches off the nodes. So would it be better to choose that, or to look at a binary thing first and then?
So it turns out that it's not something that we look at all. The branching factor is not something we consider. Instead, we only consider the number of features that we use. The number of features, which is connected to this point about relevant features. We only want to use relevant features, and we want to somehow discover a small set of relevant features that explain the data. And that corresponds to essentially the depth of the tree. Did you have a question?
Yeah, it's just us trying to avoid overfitting, basically, having our tree overfit.
That's right. I'm trying to not use the word overfit yet, but that's really what it comes down to. We don't want our tree to overfit or try too hard to explain the noise in the data. And if you use irrelevant features, you can explain any kind of noise because you might find some sort of pattern in the irrelevant feature. Yes.
So like, would it be better to find like a medium sized tree? If it's like a large tree, and then it's like a overfitting, and a small tree like meaning like a underfitting?
We haven't used the word underfitting yet either, but I know what you're saying. The question is not really about underfitting, whatever that means, but really given two trees that are equally good at representing the data, which one do you pick? And the intuition that the ID3 tries to capture is pick the smaller one. If you go below a certain depth, it turns out that you're not going to have sufficient information to even explain sufficient granularity to even explain the training data. But let's not go there yet. It turns out that if you do this, by the way, this is related to this idea of Occam's razor, where you prefer simpler explanations. But we'll spend a fair amount of time on Occam's razor sometime in the middle part of the semester. But it turns out that if you go about trying to find the smallest tree that's perfectly consistent with all the examples, finding the minimum decision tree that's consistent with the data set, it turns out is computationally intractable. It's NP-hard. If you've seen NP-hard before, you know what that means. If you have not seen it before, just think that it's computationally intractable. As the data set gets larger, we are not going to have enough time to actually search over all possible trees to find the smallest possible tree. So we can't do that. Instead, the ID3 algorithm is a recursive algorithm that's essentially a greedy heuristic that tries to find a small enough tree. There is a certain, but the choice of the best feature at the top is designed so that it favors exploring smaller trees before going to larger trees. And the only control, the only knob that the ID3 provides is this line here. How do you best split the feature? And the choice of that is dictated by this goal of trying to make the decision tree as small as possible. To illustrate this, let's look at an example. Imagine that you have a data set with 100 examples. There are only two features, A and B. Both of them are Boolean, so 0 and 1. And suppose you have 50 examples, 50 copies of that example really, where A is 0 and B is 0, 50 examples where A is 0 and B is 1, 100 examples where A is 0, A is 1 and B is 1. And it just so happens that there are no examples where A is 1 and B is 0. This is your data set. So I can, let's say the goal, we want to build a decision tree. Because there are only two features, it's easy to construct decision trees here. You can either split on an A or you can split on a B. And the question is, which attribute do we choose to split on first, A or a B? There's a question on Zoom. There's a question on Zoom. What's the convergence rate of the ID3 algorithm? When you say it cannot guarantee optimality, do you mean globally or locally? I mean globally. It does not guarantee that there is no guarantee that the tree that the ID3 algorithm picks is the smallest tree among all possible decision trees that perfectly fit the data. So there is no notion of convergence rate here because the ID3 algorithm is essentially just this simple greedy search. The number of recursive calls you can make is at most the number of features you have. But the guarantee that we do not have is that of global optimality. Okay, going back to the thing. Oh, was there someone else raise their hand? Which feature do we split on first? Someone who's not answered before. I've heard you. Anyone who's, yeah. A, good choice. Well, there are only two choices. It's a choice. And it turns out that if you split on A, you immediately partition the data into what I'm calling pure subsets. Every example where A is 1, here, every example where A is 1 is a plus, and every example where A is 0 is a minus. So we get this tree here. We could have also split on B. Turns out if you split on B, immediately after splitting, you don't get a pure subset. When B is 0, which is here and here, well, this row doesn't really count because there are no examples there. When B is 0 in the first row, you get the label minus. But when B is 1 here and here, you still have a mix of minuses and plus. So you need to split one more time. You need to split on A once again to get to perfectly agree with the data. Do you agree that both these trees represent the same data? Except when you split on A, you get a smaller tree. And going with this intuition that smaller trees might generalize better, it seems like there's an advantage for A. But instead, let's say that we have a small number of examples of this type here. Let's say we have, instead of 0 examples, we have 3 examples. Now, what attribute should we split on? You don't need to answer this because there are only 2 attributes. Let's try both of them. If I split on B, I still have the same tree, right? When B is 0, the label is minus. When B is 1, which is here and here. First of all, when B is 0, the labels are minus. And when B is 1, we still need to split on A, and you get this tree. If you split on A, it turns out you still get a tree that's structurally the same. When A is 0, the labels are minus, and here also. And when A is 1, you still need to look at B, and you can pick whether the labels are plus or minus. These 2 trees, they look the same, right? Just so happens that if one of them splitting on an A, the other one splitting on a B. Question is, which one do you pick? There are only 2 options here. So, any takers for A? You
pick A because it finds the solution the most out of exactly.
That's an interesting thought. The answer, that's a very interesting suggestion. You pick A because even with just one question, it resolves the problem. It finds the label for a larger number of examples. So if I pick A for 100 out of the 203 examples, I have the label. If I pick the root as B for only 1/4 of them, roughly, you have the label. So the suggestion is you pick the feature A because it resolves the ambiguity, the question of what the label would be, sooner for more examples. Are there other answers here? Any takers for a B? There is one person who's saying B. Yes. Why? Oh, we were never going to retrain anyway. Let's say that this is the data that you start with. Yes.
Question, would those three examples technically be classified as noise in this case?
Maybe, maybe not. We can't tell. This is the data we have.
Wouldn't it be better to then do tree B because isn't tree A technically observing that noise in that case?
Well, both of them are observing the noise, right? Both these trees give the exact same decision for the observed data. It turns out that the answer, yes.
A reason to do tree B, to start at the top, would be because on tree A, like going 1 and 0 would happen like basically never, so you have to just have a section left and not happen.
So this section is never going to happen.
It just happen very rarely.
And why is that a problem?
If you wanted to.
Oh, just the sense of elegance. Well, it turns out that the answer that was suggested is actually the right intuition here. The goal is to resolve the ambiguity as early as possible. Remember, I said we want purer partitions of the data with respect to the label. Before we had those three examples, splitting on A gave us two subsets of the two partitions of the data that were both pure. One side was all minus, one side was all plus. Well, when you split this way, this side is all minus, so 100% minus here, and here almost 100% plus. So you are nearly resolving the ambiguity even on this side. Should you choose to truncate the tree at the bottom without even looking at B, you would still be doing a good job on 200 out of 203 examples. Whereas should you choose to truncate the tree here, you are still tossing the coin on a whole bunch of them. In some sense, even though the tree that is rooted at A and the tree that is rooted at B are structurally identical, splitting on A is more sort of efficient in a certain sense because it allows you to resolve the ambiguity earlier, and in a statistical sense, it behaves like a smaller tree because most of the decisions on most examples are made early on. There is an advantage for the tree A, but we still need to quantify things. And that's where the ID3 algorithm makes a certain choice. The most popular heuristic for the decision tree learning in the decision tree learning algorithm literature is this heuristic that was invented by Quinlan called the information gain heuristic. We do not have the time to look at that today. So this is where we'll start off. On Thursday, we'll look at a formalization of the information gain heuristic, and then we'll work through an example that steps through this algorithm with the heuristic to actually build the tree for the tennis data. Then we look at generalization of that. Don't forget your homework and watch out for homework 1.